Hello everyone. We are still talking about the directed graphs, and the next problem that I'm going to solve is finding all strongly connected components over a directed graph. So in this example that you can see here, we have 6 different strongly connected components. One component here, all of them actually have been marked using this dashed line. One component here, one component here, here, and here. How to solve this problem? The first algorithm that comes to mind is using a modified version of the algorithm to check if the graph is the whole graph is strongly connected. Remember the algorithm that we discussed there was to just randomly choose a node, run the BFS or DFS from this node, and check if all the nodes are reachable from this node, then create a reverse graph, run the BFS or DFS over the same node again, and check if in the reversed graph again S can reach to all of the nodes, which means that all the nodes in the original graph can reach to S. This tells you that if the graph is strongly connected or not. We can just use the same idea here, because as you can see, every node is going to be a part of one of the strongly connected components. It's just like we are partitioning the whole graph to different groups, and those groups are all strongly connected and maximally strongly connected, those sets. So it doesn't matter which node you choose, just randomly choose one node, run the BFS and DFS, find all the nodes which are reachable, so they are candidates to be in the same connected component. Create the reverse graph, run the BFS or DFS over the same node, and find all those nodes which are reachable to S, reachable from S. So basically, and get the intersection between these two sets. So it's something like this, that you have a node S, find all the nodes which are reachable from S, and then create a reverse graph and find again all the nodes which are reachable from S, which is basically means that all those nodes have an access to S in the original graph. Okay, this is going to be set 1. This is going to be set 2. So if you are looking for the connected component that contains S, all the nodes should be reachable from each other in that, right? So just get the intersection between these two sets. After you find the connected component, remove all these nodes from the graph and just repeat the procedure. So the time complexity of this idea is the time complexity of each step of the algorithm is going to be 2 BFS or DFS. So this is going to be 2 O of n plus m plus m. And then you have to repeat it for all the number of connected components that you have. So in total, this is going to be k to multiply by n plus m, where k is the number of connected components, strongly connected components. So clearly this is not desirable. I am looking for a better algorithm, for an algorithm which is more efficient than this. So to be able to find that algorithm, let's have a deeper look at the problem. If you think about this example, this is the original example that I showed you. If you think about all the strongly connected components and think about each component as a single node, because every node in the strongly connected component are reachable from each other, right? So just collapse and merge all of those nodes in one strongly connected component and replace it with one node. The result is going to be a super graph like this. You can see that this component has just one node, so we can mark it as A. This component has two nodes, C and F. This component has two nodes, B and E. This component has 6 nodes, all the nodes I've written here, and this component has one node here. What I know about this supergraph that I got is that all the edges inside the strongly connected components have been removed, and I only have the edges between the strongly connected components from the original graph. So what is the properties of this new graph that I got? Is it possible to have a cycle in this graph? No, this graph doesn't have a cycle. This is going to be an acyclic directed graph, right? Because if you have a cycle anywhere, for example, something like this, it means that all the nodes in this connected component can have access to each other, right? And because there is an edge here, they can go and access to all the nodes here. And all the nodes here can access to each other, and one of them at least have an edge that goes back to this component. Okay, so it means that basically all the nodes in these two strongly connected component can have access to each other. So they are not a strongly connected component. All of them are going to create one strongly connected component. So it is not possible to have a cycle in the super graph that you have created here. It's just like we have simplified the graph. Okay, so if we have the strongly connected component, we could create a super graph like this. We don't have the set of strongly connected components, but by analyzing, just theoretically analyzing the properties of the supergraph, it might help us to solve the original problem, which is finding the strongly connected components. So the idea here is that if I know the sink nodes in the supergraph, here that, for example, I know that D is a part of a sink node in the supergraph. Or for example, G or H or I or J or K or L is a part of a sink node in the supergraph. The idea is that, what is a sink node first? A sink node is going to be a node in an acyclic graph. A sink node is going to be a node which the odd degree is 0. The odd degree is 0, it means that you don't have any edge going out of these nodes, right? These super nodes. So the good thing about knowing the sink node, I don't need to know all the nodes in the sink nodes. If I only know that, for example, G is a part of a sink node in the super graph, if I know it from the original graph, it helps me to solve the problem. How? I can run the DFS or BFS over G, because this is going to be, G is a part of a strongly connected component, which is a sink node in the supergraph. I know that the result of running BFS or DFS is going to be all the nodes in the same strongly connected component. If you run the BFS or DFS over G, you will visit H, J, I, K, and L, and you cannot visit anything else. The reason is that there is no edge going out of this strongly connected component. Okay, so that's it. If I know one node from a sink node in the supergraph, I can run the BFS or DFS, find all the nodes which are reachable, and I know that they are all a part of this strongly connected component. Remove them from the original graph, find another sink node, again, one node from a part of actually a sink node over the supergraph. Just repeat, just by the time complexity of O of n plus m, I can find all of the strongly connected components in the original graph. This is the idea, right? So this is great. But now the issue is that how can I find the sink node? How can I find, we don't have the super graph first. be careful, we don't have the supergraph. We just actually abstractly just thought about the supergraph and thought about the properties that the supergraph gives us, and based on that, how to treat the original graph. But now the issue is that how can I find one node which is a part of a sync node in the super graph? Okay. Now the issue is that how to find a sync node, one node which is a part of a sync node in the supergraph. The idea here is that I'm going to use DFS. I'm going to just think that maybe exactly the way that the DFS helps us to find the topological ordering for the nodes based on the finish time, maybe that's also can actually helps us here. And the reason is that the supergraph is going to be acyclic, right? When we discussed about the topological ordering, we just assumed that, okay, the graph is acyclic. Then we find this property that if we order the nodes based on their finish time in decreasing order, we can find the topological ordering over the graph. So if I run the topological ordering over the supergraph here, if I had a supergraph like this, if you run the if you run the DFS, you would actually find out that the finish time of, for example, A is going to be the largest one. So we wanted to actually see that can the finish time helps us to find the sync nodes or not, because we are interested in the sync nodes. Okay, so I have the original graph. I wanted to run the DFS over the original graph and see that can the finish time tell me something about the sync nodes or not. This is just an example of running a DFS and finish time over the nodes. You know that because we don't know anything about the graph basically. So if you start the DFS from any node here, the result of the start-finish time is going to be completely different. Here, the example that I'm showing to you is I started from A, but you can actually just run the your DFS starting from any node here. I wanted to see that what information these finish times are going to tell me. One thing that I can actually conclude here is that the finish time of the nodes in the sync node in the supergraph is going to be the smallest one, okay? But I don't actually, because you can actually have more than one sync node, and it doesn't really give you the enough information that where this actually node is. So unfortunately, finish time doesn't give me enough information to find one node in the sync node. But the finish time definitely tells me something, that the largest finish time, it doesn't matter where you actually run the DFS, where you start the DFS, the largest finish time definitely is going to be a node from a source node, not a sync node, but a source node. So it doesn't matter how you actually run your DFS, you will see that if you start from C, for example, or if you start from E, if you start from K, if you start from D or A, run the DFS and see that definitely the latest finish time will be for A. A is going to be the source node, the first source node, the only source node basically in the supergraph. So I can extract some information about the supernode, but I can't extract any information, the precise information about the sync nodes. Here, I can actually prove this. Simply, the proof is going to be based on the proof that we did for the topological ordering. The reason is that if you think about the super graph, definitely the finish time of A is going to be largest among all of them, because this is going to be the first node in the topological ordering of the super node. Okay, so I think this is clear that the latest time of any DFS that you run will belong to a node, a part of a supernode. But supernodes are not going to be useful for me to find the a strongly connected component, because if I run the DFS or BFS over A, it actually, because A is have access to some other nodes, it doesn't give me a strongly connected component of A. What can I do here is to just use that trick of reversing the edges. So in the original graph that you have, reverse all the edges and create the reverse graph, GR. What is the relationship between G and GR? And what is the relationship between the supergraph of G and GR? If you reverse all the edges, all the strongly connected components are going to maintain. So all the components that you have here are going to hold in the GR as well. So you are going to have exactly the same set of strongly connected components. I think this is quite intuitive, because you just reverse the order of the edges, but all those nodes which are connected to each other are going to remain connected to each other. The other property that we find here is that the order in the supergraph, the topological order of the supergraph, will be completely reversed, right? So it gives me, a very good thing. The source nodes in the original supergraph A will be a sink node in the supergraph of the GR, the reverse graph. And that's it. If I can find a node from a sink node, I can find a strongly connected component of that as well, right? So what can I do here is that run the DFS over the original graph, find a node which is going to be a part of a source node. Here that's going to be actually A, because the node that has the latest finish time, that's going to be one node, a part of the a source component. Then reverse the graph. Okay, over the reverse graph, run the DFS over that node. That gives you the whole component that A is actually a part of that in the original graph. Then you can actually remove it from the graph and just repeat the process. Find the next node in the original graph that has the largest finish time, latest finish time. This is going to be the next source node. That's going to be one of the nodes here. Okay, just run the DFS over the reversed graph over one of these nodes, and it gives you this component, which is a sink component in the reversed graph. Just repeat this procedure. This is going to be the full algorithm. Arbitrary pick one node, run the DFS over the original graph. It gives you a set of times, start finish time. Just keep it. Create the reverse graph. Then until the reverse graph is not empty, just find the node with the latest finish time in the original DFS that you run. Okay, that's going to be a part of a source node in the original graph, which is going to be a sink component in the reverse graph. Run the DFS over that node in the reverse graph. This is going to give you one complete component. Remove that component from the reverse graph. just repeat this procedure here. So what is the time complexity of this algorithm? It is clear that O of n plus m for the first step, O of n plus m to create the reversed graph. How about this loop that I have? You don't need to actually sort the orders based on the finish time. The idea is exactly similar to what we discussed. When you are running the DFS, whenever you finish with a node, just store it in an array. So finding the node with the largest or latest finish time can be done actually in O of 1 here, right? So this is not going to be an issue. Then running the DFS over that node is going to take only O of the number of edges in the same component, okay? And then removing all those edges from the graph. So in total, this loop that you have is going to take O of n plus m. Because for each component, the time complexity of the DFS will depend on only the number of edges in that component, not more. It's not going to visit anything else. And then removing all those edges will take the same time complexity, but in total, how many edges you have in the graph, you will visit and remove them only once. So in total, the time complexity of the whole loop here is going to be O of n plus m. The whole total time complexity is going to be O of n plus m, just a couple of the same time complexity in parallel. So this is the algorithm for the finding all strongly connected components. Try to run the algorithm over this example. Just try to run the original DFS starting from just randomly different nodes and see that those properties that we discussed holds. It doesn't matter which node you start the DFS over that. This is going to just finish this part of the lecture for this week. It is going to cover the chapter 22 and 23 in your, in the CLRS textbook, and 2 sections of DPV in the chapter 3.